Thermal expansion. Thermal expansion is the increase in the size of an object with an increase in its temperature. Here we have an increasing in one dimension. So we have a linear expansion. For example, if we have a line like this, at any shape, we have a ring. Here we have one-dimensional expansion, okay? Or we have an area expansion if we have an object with two dimensions. For example, we have a paper like this. We have A and B. If we change the temperature, so we will increase the length of this object and the height of the width of this object. We get, for example, here something like this. Here we have A prime and we have B prime. Initially we have T, finally we have T prime, so T prime is bigger than T. Okay, by increasing the temperature, we increase the volume of the area of the length of the objects. Okay, and if we have a 3 dimensions object, we have a volume expansion. For example, if we have a ball, in the case of a ball, we have a 3 dimensions. If we have any 3-dimension object, by increasing the temperature, the volume will increase. I want to study the thermal expansion of any object. Let's take first of all the linear expansion in the case of a one-dimensional object. Initially, at initial time, at initial temperature, we have an object with a length L0. If we increase the temperature to T final, we get the final length of the object, L. What is the relation between T initial and T final, L initial and L final? L final minus L initial, or delta L, equals to alpha L initial times T final minus T initial, or alpha L initial delta T. L is the final length of the object. L initial is the initial length of the object. Alpha is the coefficient of linear expansion, and T is the unit of alpha. You know here, alpha equals to delta L divided by L initial times delta T. The unit will be meter divided by meter times C. So the unit will be C minus 1. Okay? This is the unit of the coefficient of linear expansion. So this relation, delta L equals to alpha L initial delta T, is just a relation between the initial and final L and the initial and final temperature. In the case of area expansion, let's take two-dimensional object of length A and width B. Initially, we have initial temperature Ti and initial area Ai. We give a quantity of heat to the system. So we get T final and the area final. Here we have A prime and here we have B prime. What is the relation between T initial, T final, A initial, and A final? Simply, A final minus A initial equals to 2 alpha. Why 2 alpha? Because for each dimension we have alpha. Here we have alpha, and here we have alpha. Okay, so we get 2 alpha in the case of area expansion, 2 alpha times A initial delta T. Okay, so finally we get a relation delta A equals to 2 alpha A initial delta T. What about the volume expansion? Let's take here we have an object initially has T initial and we have this volume initial. Okay, we have this disk with length and width and with a thickness, we can say delta C, for example. And we give a quantity of energy to the system to get finally V final and temperature final. We can say T final, or we can say T initial plus delta T. We get the same value because T initial plus delta T equals to T final minus T initial. So T initial minus T initial equals to T final. Okay, this is the final state. What is the relation between V initial, V final, T initial, and T final? Here, V final minus V initial equals to beta V initial delta T. Okay? In this case, if we have a solid object, like this case, beta equals to 3 alpha. Okay? It's very important. But in the case of liquid or gas, beta must be given in the table. I give you the value of beta as given.